Hello everyone to the class of operating systems. Today we are discussing a very important and interesting topics in operating systems, that is deadlocks. Many of us have faced such a kind of scenario in our real worlds. Now, how is this related to operating system and what are the different actions that an operating system takes in will be the topic of discussion in today's class. So, what are we going to study in this particular chapter? We are going to understand what is meant by a deadlock, how does it occur, and what are the different ways of staying safe. That is, either can we prevent this deadlock from occurring or can we avoid the deadlocks, and we can also allow the deadlock to happen and then try to detect it and recover from them. So these are the various topics of discussions under the topic deadlock. So coming to the examples of deadlocks. So it's like very common sayings which are commonly used to explain this concept of deadlock. It takes money to make money. So if we were to start from, if we have money, then only we can make money. If we don't have, then we cannot proceed. So you are stuck. Similarly, each of these deadlocks which occur in the operating system, so operating system, as we know, is going to cater to different needs of the processes. Each process will demand for different kind of resources. It might be holding some resources and might be waiting for other resources. So if it is already holding some resource, say for example a printer, and yet another process wants the same resource, then it will not be able to execute. So either P1 cannot proceed with its execution because it is waiting for another process P2 which is holding some other resource, while P2 is waiting for process P1 to release its resource. So there is kind of a deadlock situation wherein both of these processes will not continue their execution and they are in a deadlock state. So this results basically because of sharing of resources and such as memory, various IO devices, the links, so wherever sharing is required, you will have the concept of deadlocks. So under normal operation, the resource allocations to the processes would have to go through three different steps. One is that the process has to request a resource that it requires to execute. Then after allocation of the resource, if it is granted that request, then it has to utilize that resource. After using the resource, it has to release the said resource so that it can be used by other processes. So these are the three operations that usually take place when a process requires a resource for its execution. So what is this concept of deadlock? When does it occur then? So let us consider a real world scenario here. There is a broad road and in between connecting them is a narrow bridge, and on the bridge the traffic can move either in this direction or in this direction. So one of the two processes, consider these to be different processes, either the processes here have to wait for the cars from this side to move to this side, or the processes or the cars in this case have to wait till the cars move from this side to this side. So this resource, for example the bridge, is acting like a resource which is shared by two different processes. This is just an analogy for deadlocks. So if nobody agrees for this, if these processes here don't back off, or the processes here lined up don't back off, then there will be a deadlock situation. So either the car from this end and one car from this end, they will block the bridge and no further processes or no further cars coming in will be allowed to cross the bridge. So we have to resolve this conflict. Either one car has to come back or preempt and make space for the other car, or this person has to go back. So that is the concept. Just a small simple analogy to understand the concept. So what are the necessary conditions for a deadlock to occur? We must characterize a deadlock is characterized by these 4 conditions, and all of this must happen at the same time simultaneously for a deadlock to occur in a system. What are the 4 conditions then? The first condition is of mutual exclusion. Here, one or more than one resource must be held by a process in a non-shareable mode, exclusive mode. When the resources are shareable, when multiple processes use different resources and limited resources are available, then there has to be mutual exclusion. Second is hold and wait. What happens in hold and wait? A process is holding a resource and is requesting or is waiting for another resource to be released or to be available for moving further. For example, it is having a hard disk or a drive available to it. Now it is waiting for a printer to be available to proceed further. So this condition is called as hold and wait. And no preemption, in the sense nobody is going to release their resources unless they complete their task. So there is no forcible preemption of resources and a circular wait. So it results in a cycle formation. Process A is waiting for a process B. Process B is waiting for process C. C is waiting for A, for example. It results in a cyclic formation. Each of this is waiting, each process is waiting for another process to complete its execution, and nobody actually completes the execution because there is a circular wait condition, and hence leading to deadlock. So all of these occurring simultaneously in a system will lead to deadlock condition. So how do we understand this? How do we proceed further to analyze this? So for that we have a resource allocation graph. It's just a visual or mathematical way to determine if a deadlock has or may occur. So it's just a graph. A graph may have a set of vertices indicated by V. V in this case are nothing but the processes. The nodes act here as processes. So P1, P2, P3, P4, Pn. There might be n processes and there might be multiple resources also. Different types of resources. And the edges, various kinds of edges are present. One edge may be pointing from the process to the resource or from the resource to the process. So two different types of edges. One is called as requesting edge and the other is called as allocation edge. So how do we represent this graphically? Here process is indicated in a circle, using a circle with the process number. A resource is indicated as a square resource type. The dots here or the blocks, small blocks, indicate how many instances of that resources are available. Here the 4 dots indicate 4 resources are available. So the edge from P to R indicates that P is requesting one instance of Rj. Process P wants or requires one instance of resource Rj. This edge from R to P indicates that resource Rj, one instance of resource Rj has been allocated to Pi, that is Pi holds one instance of Rj. Moving on further, let us consider a very simple example. So from this resource allocation graph, what do we find out? What is that we can figure out? That process, there are 3 processes existing, 1, 2, 3. There are different types of resources, R1, R2, R1, R2, R3 and R4. R1 is having a single instance, R2 is having 2 instances, R3 is having a single instance and R4 is having 3 instances. From the graph we understand that process P1 is requesting a process or a resource R1. Now R1 is already allocated to P2. P2 is requesting resource R3 which is already allocated to P3. So this is assigned, R3 is assigned or allocated to P3. This is requesting, P2 is requesting R3. Similarly, one instance of resource R2 has been allocated to P1. One instance of resource R2 has been allocated to P2. So this is, if now we will check whether there is a cycle, whether there is a deadlock present in this system. We will check whether there is a cycle formation present here. At present, in this case, P1, R1, P2, R3, P3. Then coming back, P1, R1, P2, this. So at present, there are no cycle existing and the system is not having any deadlock. Now consider another resource allocation graph. Say suppose P3 is requesting one instance of resource R2. In this case, now you check for the cycles. P1 has already been allocated with R2. It's holding one resource of R2. P1 is requested for R1. R1 is being held by P2. P2 is requesting R3. R3 is being held by P3 and P3 is waiting for R2. So there is a cycle formation, a closed loop structure kind of thing. One process waiting for another process. It leads to a circular waiting condition. So this is called as hold and wait condition, and you can see there is a cycle formation, and hence we can say that the system is not in the safe state. Here there is one more example indicating there are process P1, P2, P3, P4, R1 there are 2 instances. One is allocated to P2, one more is allocated to P3. P3 wants R2 to be released. As you can see, there is a cycle formation here. So this system also leads to kind of deadlocks. There is a cycle here. Resource allocation graph is having a cycle, but there will be no deadlock. Why there will be no deadlock? Because there is a possibility later that process P4 may complete its execution. Once it completes this execution, it will release this instance R2, which can be further allocated to P3. Fine, and hence although there is a cycle present, there might be no possibility of deadlock. Maybe that the system or the process has to wait. So what are the general strategies employed to handle the deadlocks? There are 3 different generic ways in which deadlocks are usually handled. The first and the easiest way is to ignore the deadlocks, and most of the operating systems do this. We simply shut down the system and restart or reboot the system. But this is not useful in more critical operations. It's not suggested that we will be able to shut down the system and again begin all over fresh again. But for trivial kind of operations, we can certainly go for this method, because the overhead which is involved in dealing with deadlocks is certainly more when it comes to dealing and prevention scheme. So wherever possible, we can ignore the deadlocks as if they never occurred. There is another scheme where we try to prevent the deadlocks from occurring. So how do we make this? We see to it that the 4 conditions which we have just now seen, that is mutual exclusion, hold and wait, and circular wait, and no preemption. All of these should not happen at the same time. If we are able to eliminate any one of the conditions, then we can prevent the deadlock from happening. Similarly, avoidance. We need to have little more additional knowledge about the processes, the number of processes in the system, what are the resources that they are going to demand, and with this additional resource or information, we can run an algorithm which will test the system will be in safe state or unsafe state if the allocation is done, and hence we can avoid the allocation of those resources to the processes. So either we can prevent, or we can avoid, or we can ignore, or we can allow the deadlock to happen and then deal with it. We have to understand that after once it allows to occur, we should be able to detect that a deadlock has occurred. Once we are able to detect, we should know how to get back to the normal state or how to get back the resources. There are various policies followed here. So deadlock prevention, as we said, we are going to avoid any of the 1 conditions. For example, mutual exclusion. Wherever it is possible, we will try not to use the mutual exclusion. Wherever we have shared entities, for example, read-only files, we do not require a mutual exclusion to be employed for this, where 2 processes can read simultaneously. So that type of processes can have this mutual. It's not necessary to have mutual exclusion. Also, hold and wait. We can collect information as to how many resources are required by that particular process even before it starts for execution. So the only thing here is we will be utilizing the resources in a very poor fashion. The resource utilization will be very low, because say for example a process P1 may be requiring to read from the disk drive, maybe it has to, from a CD drive it requires to read a file, and then it has to do certain operations on that file which is being read. It has to sort or do some mathematical calculations, store back that file onto the hard disk, and then print the changed results. So in this approach, what the process will do, it will acquire a CD drive, it will also request for the secondary drive, also it will request for a printer. So in this case, printing operation is only done at the end, but it is still holding that resource, although it is not required at the very beginning of the process. So the utilization of the resources is going to be very low. Also, many other processes will be starved. It will lead to starvation for other processes, because if this process is going to take lot of time, the other process have to spend their time just waiting for the resource to be available. So this is, but we can still certainly prevent this at some cost. And one more is no preemption. So if we are able to allow preemption, if there is any process which is requesting for a resource, then we will either preempt it, in the sense forcibly release the resource and allocate it to another resource. So that can be also done to prevent the deadlock from occurring. and we can avoid the circular wait condition. So we will see how many resources are present and how many processes are present. The request will be granted only when the request is placed, the number of resources, and the request is placed in an ascending order. So each of these techniques, any one of these techniques can be used to prevent the deadlocks. Further on, we may also try to avoid the deadlock from happening. We can keep the system in the safe state. Safe state in the sense that we will have a sequence of processes will be existing such that there are a lot of resources for them to start and finish their process, and once they are finished they are going to release those resources back to the operating system. Unsafe state may lead to deadlock, and in the deadlock state there is no progress made. It is like kind of stuck position. So this is a pictorial representation of different types of states. One is a safe state. Here we can avoid the deadlock altogether. In unsafe state, we will be having in certain cases deadlocks. Unsafe state does not necessarily mean deadlock will occur. All unsafes are not deadlocks. So there are various deadlock avoidance schemes. So just let us consider one example and see here, can we find a safe sequence to execute these three processes. This is a snapshot of a system taken, and there are three processes shown here: P0, P1, P2. P0 requires 10 tape drives. There are total of 12 tape drives present here. Multiple resources are present of tape drives, instances of the same resource type 12 are present. Out of that, P0 would require maximum 10, P1 would require 4, P2 would maximum require 9 resources. And at the moment, P0 has been allocated 5 tape drives, so remaining would be 10 minus 5. Still it requires 5 more for its needs to be satisfied. Here it is allocated only 2, so it requires 2 more. Similarly, P2 is allocated with 2 tape drives, whereas it requires 9. So how much is the current need? 9 minus 2, which is nothing but 7. So now P2 requests, so totally how many are allocated? As you can see, 5 plus 2 plus 2. 9 tape drives are allocated. Now if P2 requests and is given one more tape drive, what would happen? One more tape drive, can it be given to P2? Yes, surely it can be given, because still there are remaining, out of 12 you have only allocated 9. There are 3 more tape drives available and one can be surely allocated to P2. So taking in advance, we need to know the state of the system, we need to know its maximum requirement, the current requirement, then we can decide whether the request made by the processes can be granted or not. So there is a algorithm called as safety algorithm which checks for these different types of states. There are 3 variables used in this algorithm, that is need, work and finish. Initially, we will always check before we are going to allocate to new process any resources, we are going to check whether the need is less than available plus allocated to that particular process. If yes, then we are going to proceed further. So we are going to analyze this. We are going to initialize work is equal to available. There is a vector which is a finish vector which is set to false for all the processes. Initially none of the processes have completed, so we are going to set it to false. Then for each process, for each I, find an I such that finish of I, if it is equal to false, because initially they are not yet completed, they have to be false. Then the need has to be less than the available, because work is nothing but available. So if available resources are less and need is more, we can't grant that request. So this condition has to be met. So if there is no such process, then we have to go to step number 4. That means the resources have finished its execution and set the finish flag is equal to true. If this is not, if there is no such I existing, then what we are doing, we can allocate that or grant that request by work plus allocation. New work matrix will be, now you allocate the requested resources to available resources and we present it. So the available should be less now and finish flag will be set equal to true, and we continue this for all the processes. Consider here a very simple example. We have 3 processes P0 to P4 and there are 3 different types of resources A, B, C. Totally A has 10 instances, B has 5 instances, C has 7 instances. And this is the snapshot of the system chart which is taken at some time t. Now we need to find whether there is a safe sequence existing which can satisfy these requirements, these needs, the requests which are made. So we have to every time check how much is the maximum need, and that we do by allocated and can be requested, and available is only 333. How did we get this? We have 10 of A. So as you can see, 2 under A, all these different processes have been allocated 2 plus 3, 5, 5 plus 2, 7. So 7 resources of type A has been already allocated. Hence the available resources is 10 minus 7, that is nothing but 3. Similarly, B type has 5 total resources, 5 minus 1, 2, 3 is available. And similarly, C has 7 instances of resources, and out of that it has allocated 5 of them. So 7 minus 5, remaining is 2 available to be allocated, and we run the safety algorithm and check whether we are able to find out a particular safety sequence. If yes, then we are saying that the system is in safe state and deadlock will not occur. So this is what we are trying to run. Moving on further, here the deadlocks detection, if the deadlocks are allowed to occur, then what is done? So here when we talk about the resource allocation graph, there is something called as wait for graph. When we have a single instance of a resource type, we use a wait for graph. Here that wait for graph is obtained from the resource allocation graph. P1, we are simply collapsing the edges, we are removing the resources from the graph and collapsing the resource edge to the process edge. So effectively what this means, P1 is requesting R1 which is being currently held by P2. So effectively P1 is waiting for P2. So I can directly say that P1 is waiting for P2. So this edge P1 is waiting for P2. 4 processes are there, P1, P2, P3, P4, P5. So removing these resources and collapsing the edges, we obtain this. So P2 to P5, P2 to P5, removing R3, P2 to P3, P2 to P3, removing R2, P3 to P4, removing R5, P3 to P4, and P4 to P1, removing R2. So check if there is a cycle existing, and we can see that there is a cycle. A cycle in this case indicates that there will be a deadlock. So how do we work out this, we are going to keep a track of how many resources are available, how many are already allocated to the processes, and what is the number of requests made by the process. We are going to use the same safety algorithm with a little modification. Instead of the need matrix, we are now going to use the request matrix and work out the same algorithm again. So here we can see initially, let us consider whether this is a snapshot of the allocation of resources, and these are the requests that are made. So at a time t, this is the snapshot, P naught has been allocated 0 of A type, 1 of B type and 0 of C type resources. It has not made any new requests, so 0 0 0. And available also, there are no resources available, already all the resources available have been allocated. Now whether this is going to work out, how are we going to detect a deadlock in this case, whether the system is in safe state or is there a deadlock, how are we going to find this out? For that we are going to check out the different sequences. Initially check out which processes request can be satisfied. Available is 0 0 0. We can see from this graph that P0 and P2 can be satisfied with this availability because they don't require any more the resources. So say that P1 finishes its execution and then it releases these resources. So I am adding this resources now to the available pool. The new value will be 0 1 0 because I am releasing the resources now. So when I release, one B type resource will be made available. It is free now to be used by other processes. Similarly, which other process can I satisfy? I can still satisfy this because P2 is completed, and after completion I will be releasing these resources. So 3 0 3, that means 3 of type A has been released and 3 resources of type C has been released, and already B type P0 has released 1 resources. So total available resources then would be 3 1 3. Now with the available 3 1 3 new available, check whether can we satisfy any other requests made. Can we satisfy this request, P1's request? Yes, of course, because we have 3 of A type and 3 of B type, we can satisfy P1. After satisfying P1, it will also lead to completion. It will release back those resources and that resources will be added to the pool and the process continues. So we can say that we would find a safe sequence and the system is not in deadlock state. There is no deadlock detected here. What if a new request is made by P2 of type C? So if this would be changed to 0 0 1, then what would be the case? As we can see, there will be a deadlock situation in this case because it can only satisfy P0 with this state. So there will be a deadlock which will occur whenever P2 requests for one more resource. Then how do we recover? Once we understand that there is a deadlock has been detected, then how we recover from the deadlock? We can recover in different ways. One is we terminate the process. We would kill all the processes, but this would lead to this solution is very expensive, not suggested because many processes might have reached their completion, and again terminating them means again starting fresh. So this would be a very expensive solution. Then there is another scheme which we can choose where we go on killing the process which has consumed very less time, or we can select based on priority, time of completion, needed time of completion, and so on. Or we can preempt the resources and terminate that particular process. So whose process where we can, whose resource we have to take back, forcibly preempt whose resource. So we have to select a victim, and that again depends on different conditions, which process to select, from whom to release the resources. So these might be little costly solutions, but nevertheless they can still be helping us to recover from deadlocks. So combined approach can be used. So there is no one approach which is best suited for deadlock recovery. We can make a combination of all these approaches and see to it that the system recovers from the deadlocks. So in this section we have seen what are the necessary conditions for a deadlock to occur, and we have seen how a deadlock occurs, the characteristics of the deadlock, and under what conditions they occur, how to avoid them, how to prevent them, and if we are allowing a deadlock to occur, how to detect and also recover from the deadlocks. Next class we would do a working example based on the safety algorithm as well as the banker's algorithm. Thank you.